Hi guys, today we are going to get started looking a little bit more closely at forces. Remember, that's our theme for the whole year, is to look at forces in different contexts. So this is where we're going to start learning how to diagram and draw the way that you'll expected to do so at Dobbins Bennett in the physics classes. We're going to learn a little bit about some different types of forces, and we're going to learn how to model what happens when those forces act on different objects. So if you'll go to a clean page in your scientist notebook in your notes section, and remember that wherever you see a pencil, then that means that there is important information on that slide that I want you to have as part of your notebook. Okay. All right. Oh, look, we've got a box, and this little thing is pulling, and that one's pushing. And I don't know if that box is moving, but here we go. All right. So let's start at the beginning. All right. So, what is a force? Well, you could probably tell just from looking at this. Guess what? A force is either a push or a pull. So it's a push or a pull on an object, but there's a little bit more than that. We say a force is a push or a pull, but it provides energy to do something. And what do we want things to do? We want things to move. And so if something starts moving or stops moving or changes direction, we know that it has had a net force applied to it in some way. So in physics, a force is anything that makes an object accelerate. Now, here comes those vectors again. All right. Now, remember, we said that we use vectors when we want to, or these arrows, when we need to represent something that has both a magnitude and a direction. So, velocity has a magnitude and a direction, acceleration has a magnitude and a direction. Well, forces have magnitudes and direction. And so we also use these vectors to represent them. Sorry, my throat's getting weird today. I'll have to drink some more Diet Mountain Dew. And that's because, think about it, it matters not only how hard you push or pull, so that's the magnitude of the force, but it's also going to matter in what direction you're pushing or pulling. And so that's why we need vectors. Forces always come in pairs. Now, we're going to state that here, and then we're going to come back to that in a couple of weeks. But forces always come in pairs, and we measure forces in something called a Newton. Now, really, what we're measuring with those Newtons is the energy that results from that force. But for us in eighth grade, we're just going to say, hey, we measure force in newtons, named after Isaac Newton, and we put a capital N. So to give you an idea, if you had an apple in your hand, and you wanted to lift that apple up a couple of feet up in the air. So you're just holding it out, you're holding like your arm straight out, you've got an apple, and then you're just going to lift that apple up. That probably takes about 1 Newton of energy to do that motion. Okay. All right. Now, if we have forces acting on an object and they are balanced, then our object is not going to have any change in motion. So here's a box, and we have this little weird, funny, strange man with very odd feet pushing in this direction, and this is the vector to represent the force. So this is direction and magnitude. And we have this equally odd looking little man that apparently is missing his neck, pushing in this direction. Notice it's an opposite direction, but it's equal in magnitude. Well, basically, we would say those kind of cancel each other out. And if they cancel each other out, then that object isn't going to move. It's going to sit right there. That's because the forces are balanced. This is an example, and you can click and play this. We can't do it this year because we're trying to not, touch each other with the pandemic, but I actually have had students in the past do this. So you can click and watch this example of some ladies attempting to stay and have their forces balanced. Okay, so you can click and watch that on your own. But here is a great drawing to kind of give us this idea again of what happens with balanced forces. Here's my little bison buffalo. Well, he's not that little. Here he is. I guess it's a he. And if this one on the left is pushing this direction with 500 newtons of force, and this bison on the right is pushing this way with 500 newtons of force, then what will happen? Nothing. They're just going to sit there and push each other. They're not going to be moving. You'd think they'd get tired maybe, but they won't move in either direction if the force is exactly opposite. Now, if one of them has 499 newtons of force, there's going to be something happen, but if it's exactly opposite and equal, no motion. No change in motion. I'm going to correct myself. No change in motion. All right, so if we were going to draw this in physics, this is how we draw these things. Isn't it funny? We always just draw a box to represent any object we want. I mean, isn't that weird? But I love it because I don't draw well. So like I'm big on this. Like, yeah, I can draw a box. So there's a box. If I was going to represent that bison system, in other words, what's going on, I would just draw a lovely little box right there. And I would draw an arrow this direction with 500 newtons. And then I would draw an arrow that is equal in size and opposite 500 newtons to the left. And what I'm showing here is that this and that cancel each other out. And so that object isn't moving. So we represent in physics any object we want to talk about. We're going to represent it by drawing a box, and then we draw our vectors to represent the direction and magnitude of the forces. Here's another example, and this is why a second ago I corrected myself and I said change in motion. Well, this is why I caught myself. So listen really carefully. This car is in motion. It's moving with a velocity. Now remember, we also can, in everyday language, we tend to use the words speed and velocity to mean the same thing. We know they don't, but we tend to say that, of 20 meters per second. All right, the car is moving with a velocity of 20 meters per second. Now, there is a forward force on this car. This car has an applied force from its motor, right? There it goes. But it's also got some forces in this direction as well, maybe from the friction between the tires and the road or some air resistance. But I want you to notice that the forces are balanced. The forces are balanced. And the question is, what will happen? The answer to that, a lot of kids get this wrong, and they would say, well, it will stop. The car will stop. No. Remember, I said if the forces are balanced, they won't cause a change in motion. If the forces are balanced, there is no change in motion. If this car is going at a speed of 20 meters per second and the forces are balanced, the car will still just keep moving at 20 meters per second because there's no change in the motion. So for balanced forces, here's your pencil. If the forces on an object are balanced, if it is a stationary object, it's not moving, it stays still. But if it's a moving object and the forces are balanced, the object will continue to move at the same speed and in the same direction. So what about if the forces aren't balanced? So you can click and watch this for a little bit. I did not know such a thing existed. And there might be a more recent video, but this is the 2014 World Indoor Championships. And yes, it is a tug of war. And if you click and watch that, you're going to see for quite a while, the forces are pretty balanced, but then they're not balanced. So you can click and watch that. So here's what happens if we have unbalanced forces. Here's our truck, and again, it's got a vector indicating that it has a force of 100 newtons that is acting on this truck to the right. And I notice over here it has a smaller force of 60 newtons. See, the arrow is not as long, acting on this truck to the left. Well, they're opposite, but they're not equal. So what's going to happen now? Well, here's the deal. If there's 100 newtons acting on this truck to the right and only 60 newtons acting on this truck to the left, then I'm going to end up with some leftover force. 100 minus 60 is 40. I've got some leftover force of 40 newtons acting on this truck to the right. And so that truck would start to move, or it would speed up, it would accelerate to the right. If the forces on an object are unbalanced, if it's a stationary object, it will start to move in the direction of the net force. If it's an object that's already moving, then the object is going to change speed or direction in the direction of the net force. So an unbalanced force results in acceleration. So let me click back again. Oh, I hate when it does that, guys. Let me get it. There it goes. So right here, if the truck was stationary and not moving, and these are the forces on them, then the truck would begin moving in this direction because of that net force of leftover force, net force of 40 newtons. If the truck is already in motion, but we still have this scenario of forces, I'm going to still have a change in the motion of this truck. I'm going to have a change in the motion of this truck. It would accelerate to the right. So you've heard me already use this word net force, and I called it leftover force. Whether an object has a change in motion depends on the net force on the object. And the net force, like I said, my everyday language for it is, ooh, it's the leftover force when I subtract everything from it. But really, here's the technical term. The net force is the vector sum of all the forces acting on the same object. And at Dobbin's Minute, guys, I'm going to tell you in the physics classroom there, you're going to get into some more directional components with negative numbers and things. And so they're going to be real picky that you are always talking about a vector sum. I'm going to tell you for 8th grade, just for us to conceptually understand what's going on here, that means like just kind of get our beginning thinking in our heads. We're going to be okay with kind of the way we're going to teach you, which is just figuring out what our leftover force is. So remember I said in physics, we represent objects with boxes. And so here's an object represented with a box. And this object has two forces acting on it. The forces are acting on it in these directions. And each one has a 10 Newton force. So the net force is 20 newtons, and the object would accelerate to the right because it's going to accelerate in the direction of the arrow. Here's another one. This one's a little trickier. I have a 5 Newton force and a 10 Newton force in this direction, and I have an 8 Newton force in this direction. So the net force, 10 and 5, that's 15 newtons in this direction, but only 8 newtons in that direction. And 15 minus 8 is 7, last time I looked. So the net force is 7 newtons, and the object would accelerate to the right because that leftover 7 newtons came from these two forces, which are to the right. So the object would accelerate to the right. Here's another one. We have a 20 Newton force to the right. We have two forces to the left, 40 newtons and 5. So to find the net force, it would be 40 plus 5 is 45, minus the 20, and the net force is 25 newtons, and the object this time is going to accelerate to the left. Follow the direction of these arrows. The leftover force, bigger, larger force, is over here pushing to the left, and the object would accelerate to the left. This is pretty funny. It's been a few weeks since I made this. I'm like, there's a pencil, there's a box. All right, wonder what's coming up. What's coming up? Oh, there's a force on the box to the right. What's next? Oh, an opposing force on the box or the object to the left. Well, this is unbalanced because that arrow, that vector, is not as long as that one. So that's unbalanced forces. Equals acceleration. Oh, that was cute. I liked that. Okay. So I think what I wanted you to do was write unbalanced forces, put this example in, and write the word acceleration. Okay. Ooh, object. Oh, here they are again. They didn't go away. Back to these ticker tape. All right. So this time we're throwing in something else, though. All right, so let's look at this. We want you to tell us, look, would these forces be balanced or unbalanced? So let's look. Here's the first one. Starts out close together and then gets further apart. So that tells me that this car is speeding up. It is accelerating to the right. If it's accelerating, that tells me there has to be unbalanced forces on it because there is a change in its motion. This one is representing constant because there's an equal space in between them. This is representing constant motion. And so since it's not speeding up or slowing down, and I'm going to assume not changing direction, this would represent balanced forces, no change in motion. This one I'm having to look at pretty closely, but it looks to me like they are getting closer together. I think from here to here is not as far apart as from here to here. So I'm going to assume this one is slowing down. If it is slowing down, then it has to have unbalanced forces on it to cause a change in motion. Oh, the first car must have unbalanced forces acting on it. I know this because I can see the cars accelerating. The other two cars both have balanced forces because they're moving at a constant speed. Okay. So now, remember, it's time to write your summary. It's really important to us that you take the time to write these summaries and to look back over your notes. Again, many of you are very comfortable writing your own summaries, but for those of you who need a little support, we kind of just put some sentence starters in here to help you. So you can write a force is, and then go back in your notes and look and see what you need to add to complete this. Forces always come in pairs. Forces can be balanced or unbalanced. If the forces on an object are balanced, then tell me what happens to the motion. If the forces on an object are unbalanced, tell me what happens. I'd like to know what net force is. And we represent forces by drawing. So if you need support, you can use these sentence starters and complete this for your summary.